So primarily we talked about digital system design and what does it mean once we say digital systems, and from our perspective or this course perspective, it is mapping something which is usually done in software and you map it in hardware. We say that's the digital system from our perspective. So you're taking an application and mapping it on it depends, you can get an ASIC, application specific integrated circuit, developed for a particular application, or for our case you map it on an FPGA, right? And this is what mostly the case is, that we map an application on an FPGA. But then there are ASICs. You can always find any standard algorithm which prevail in industry, you will find there is an ASIC for it. For example, MPEG. So you find there are MPEG ASICs, though people can do it in software, but MPEG ASIC will be very cheap, okay? It will be very convenient, it will be power efficient, it will be low in cost. There's so many reasons why people, it's a very natural process through which a software gets into an ASIC once it is standard. So people start making an off-the-shelf component for it, right? If it is not standard, then and still you require it to be done in hardware, you map it on an FPGA. So should take a problem, and then I highlighted the contents, the course contents. Let me see if I can. I think this has been uploaded on the website as well, but as I have not shown you this, so let me just quickly show you what I intend to cover in this course, and that should just cover the entire spectrum of digital design. So these are the topic-wise outline, and let me try to maximize it so that it has all the requisite information what we discussed last time. So we'll go in a procedurally to learn all these skills in this course, learning about the top level design, then the languages, all the languages which are used to design, to model, and they are the Verilog, System C. We'll briefly touch the other two languages as well, and then spending some time on top level design, that how usually you design the top level, then going down into, and as we need to map it on FPGAs, then we'll spend time learning about what powers FPGA offer, and FPGAs today from different vendors, choosing one over the other. And then we'll go over and discuss the all the techniques which usually we exercise to design effective architecture, and they help you at the back of your mind. The problem is independent of the technique you use, but they help to come up with an interesting, optimized, intelligent architecture. So today I intend to cover from this perspective hardware description languages, and we'll spend more time learning about Verilog, though I'll very quickly go over Verilog. But what I intend to do is to let Ali take a workshop. So those of you who are not very expert or they have not seen Verilog, they can spend more time with Ali in the lab, so that you do some hands-on, do some exercises. So we'll plan a workshop also on Verilog, but here I'll try to just quickly cover it, so that we just cover it, and then you spend more time with him if you have any question, queries, because all the assignments in this course, they have to be done on Verilog. So Verilog you need to know. So Verilog, as it says, it's C-like language, but one problem which I see even in professionals, once they are programming in Verilog, they are carried away and they take Verilog as a programming language, not a hardware description language. It's a very common problem I have seen, because it's powerful. So they have something in mind, an algorithm, so they just sit down and start coding algorithm, not realizing what that algorithm will actually get synthesized into. And that's a very major problem. Once they synthesize, we find out it's taking 40% of the FPGA, a small design which we ask somebody to do, because he is not keeping that perspective of Verilog in mind, that Verilog, whatever you write, a single line of code means something in hardware. You write a for loop, for example. So in other languages, it's very convenient to write for loop, and even in Verilog it is very convenient to write for loop, and I'll give you a few example. Once you in Verilog you write for I is equal to 0, I is less than 10, I is equal to I plus 1. Okay, this means that you are replicating that piece of hardware 10 times. It's not the statement which will run 10 times, the same statement which will run 10 times. It is the convenience Verilog is giving you, that if you are replicating something 10 times, you can put it in a for loop. But it does not mean that same thing will be running 10 times as it happens in software. So that is the difference which you always need to keep in mind, that you calling something 10 times mean you are making 10 copies of the hardware. Okay, 10 copies of the hardware. A for loop means 10 copies of the hardware. If there is a function, so you define a function in Verilog, any function. So as you do in C function means something very different. A common code you write at one place so that whenever you intend to call it, your program flow goes there, execute it and comes back. But in C, in Verilog, function means hardware. If you are calling it 10 times, it means the hardware gets replicated 10 times. Writing function does not mean that this is done once, and every time hardware requires that function to be executed, it'll go there, execute that function, it'll come back. No, it is not. It does not happen like this in Verilog, and that's what I am stressing, emphasizing. And this is the most common misconception I see in engineers and designers, that they don't understand this difference between C and Verilog. That in Verilog everything you write is hardware. Okay, for loop, replication. Function calling so many times, replication. It's just making that piece of hardware. If you are calling that function 10 times, the hardware gets replicated 10 times. It's a very major difference, and that is something. A compact code written like in few lines does not mean small hardware. Sometimes you write very compact, very nice Verilog code. It is just helping the simulator to simulate it in a better fashion. That's it. A compact code gets executed fast on a simulator, but hardware will just start unrolling. The synthesis tool will start unrolling all the for loop, all the function calls, and so this is why I have written in text and quotes, because my own words, that you must visualize hardware in your mind while you are coding things in Verilog. That's very important. Right? And we will see that how you do that. It's very simple, and because if you just adhere to guidelines, and you will always just follow those guidelines, it'll help you to know what you are doing actually, and because it's something, it has a consequence. So this is a typical flow in designing algorithms in hardware, that you first focus on algorithms. You develop algorithms, and once you are developing algorithms, you don't want to bother people to worry about hardware, that whether it will get implemented in hardware. There are usually different people who are working on algorithms. Sometimes it is better for them to know that this is something they are developing, it needs to go in hardware. So hardware affinity, like developing algorithm, they are hardware friendly, is very important, because in hardware, if you are dividing so many times, it's so impossible. You are asking or giving an impossible task to somebody to put so many dividers. So division is usually avoided. So we try to figure out ways where there are many minimum divisions. Okay, so and that's something which the algorithm developer needs to keep in mind. Maybe a very small code written which has division and square roots and fancy logs and exponentials, very hard to do in hardware. So that he should have this in perspective. So algorithms are developed, and then and we'll spend some time in also giving guidelines to those people who are actually developing algorithms, so that it goes smoothly in the design flow of a system, that you design algorithms, but algorithms should be structured in a way they are easily portable in hardware. So person who is testing, the testing becomes very critical. A MATLAB code not written with this perspective, it's very hard for people to come and test it, because it's doing something else, the variable names are different, and the whole thing you can do only black box testing. You run something in MATLAB, get the result, you run something in Verilog, get the result and test it. You cannot get inside the things to see where the actual problem is. It becomes very, very critical, and those of us who are actually struggling with these things, we know that you spend days just figuring out a very small bug you have in the code and which is not matching with the MATLAB. So we'll adhere to those guidelines as well, and we do software hardware partitioning. Usually a team of engineers who are porting algorithms in software, and there are other who are designing hardware for those algorithms. Going through this route, you take the algorithm, convert them in fixed point, code it in RTL Verilog, do the functional verification, do the synthesis, generate lists, do the timing, see whether the timings you're happy with the timing or not. If not, you either redesign or resynthesize, changing the constraints. And once you are happy, you download the bit files, or if you're designing an ASIC, you send it for layout, so you get the laid out chip, and then you do the system integration. But as a matter of fact, the integration and testing is happening in every stage of the design. So this is a system level design flow, and just the same description that how this happens, and as I mentioned, I will spend time on this. Then another thing which is happening, because designs are becoming more and more complex, right? And the complexity usually is in interfaces, and interfaces are very difficult to program, very difficult to make the interface between two devices work. And the challenges are in interfaces. So, and for example, if you have a device, maybe a digital signal processor, it is talking to another device on an interface, there are very stringent protocols that you need to adhere in order to make something go from one device to another device. You know, you need to send a request, and in those many cycles you must get a grant, then you get the bus, then you do this, you do that. So at RTL level it is very complex to model or to design the interfaces. So people are saying, if you start worrying about the interfaces right at the start, it becomes very difficult you to get into the details of the design. So they have come up with another design methodology, and which is quickly taking over, that it's a transaction level modeling. And transaction level means that you don't worry about the actual hardware detail of the interface. You say this amount of data goes from this device to this device. So you make a transaction of data to an actual device. Okay. So as you see, this is a transaction level model, where this is a transactor, and transactor is primarily runs a C, you generate your test vectors, and you load it into your device at the transaction level. You're making a transaction, not the RTL level detail of how actually this data goes from one device to another device. So you do transaction level modeling so that you focus more on the actual algorithms. So at the same time, once you are doing transaction level modeling, there are people who are trying to make the interface work, the RTL and the actual coding, and you know. So, and then once you have the actual interface, and as you can see, there are only two lines which shows you put something in the device and you take something from the device at the transaction level. But once you know that your interface is working, then you go and integrate. You need to write drivers and transactor, which basically you go into the details. Obviously you have to come to this point, but people are trying to avoid going to this unless they are, you know, sure that their designs are working, and independently they are working on the transaction. So the transaction level is another design level where you are not worrying about the interprocessor communication, and you are moving data at the transaction level. RTL is more detailed, and this is what makes RTL very complex to comprehend. RTL means register transfer level. It's very simple definition, and we need to understand this. A register transfer level means you need to know all the registers in your hardware, and that's the challenge. Okay? You need to know all the registers. Where are your registers? How many of them are there? Where are they placed? If you know all your registers in your design, it means you are coding at RTL level. People usually don't comprehend this. This is something very important, that at RTL level means that it's not something you have coded and it's working or not working. No, RTL level means that you know where your registers are. You know each and every register. If there are 500 of them, you know where they are, and you have intentionally created all those registers. You know, it's not that code has automatically, because you were doing something automatically, that they got created. So register transfer level is, and that's how we program. So the hardware design is done at RTL level. If only we understand this much, that once we are designing something, even on the paper, we need to know where our registers are. And once actually we are coding, we need to code our registers in a different manner, and all the functionalities in the combinational cloud. So the combinational clouds are coded differently. So the cloud you see is the functionality. Whether you are adding, subtracting, shifting, you know, anything you are doing, and you do something in hardware, and you store it in a register. That's what you have to do. In hardware, that's what you are doing. You cannot just have everything in a cloud, and there are reasons, and we'll see why. So you do something, you put things in a register, then again you do something, you put something in a register, you do things, put things in a register. So it can be perceived, your design can be perceived as many clouds and many registers. And you need not to get into the clouds, and that's the level of abstraction, the comfort you get. That at RTL level, you are not worried about AND, OR gate, XOR gate, flip-flop, this or that. You know this is the functionality which you have, and these are the registers. So you are done. If you know at that level of detail, you're working at this level of detail, you are done with the design and the coding. And the coding also becomes very simple. And why you have to just put registers after a little cloud, you have to put a register. The reason is that you want to run your design at a very fast clock. That is the performance. You say this Pentium runs at 3 gigahertz. What does it mean? Like there are clouds in the Pentium, the combinational logic, that no combinational logic is taking more time than 3 gigahertz, mean 1 over 3 into 1 over 3 into 10 raised to the power minus 9. So that's the time. No combinational logic in a Pentium processor is taking more time than this much. So all the gates, as this transparency or the slide shows, that the combination logic is made up of gates, and you are not worried about what gates and how it actually gets implemented, but you need to only understand that combination logic consists of gates, and every gate has a delay, because gates are made up of transistors, and every transistor, once it switches from 0 to 1, it will take some time. Okay, every transistor, once it switches from 0 to 1, it will take some time. So many of these transistors in a path will take more time, because unless all the paths in the design are settled, as we show, this is the longest path. And what happens usually, there are paths, like billions of paths in your design. There are paths which are shorter. For example, you trace this path has 1 gate and 2 gate. So a signal traveling on this path will get settled here quicker than a signal which has to pass through 1 gate, 2 gate, 3 gate, 4 gate, 5 gate. So it will take more time. It means the answer here will not be stable unless the slowest signal, which is going through so many gates, gets at the output. Unless that signal reaches at the output, you will not get just a consistent answer. Answer will be switching. For example, if it is 0 and the signal has not yet reached here, you get 1 here. But once this signal reaches here, it switches from 0 to 1, and then you get 0 here. So stable 0 means that all the signals moving from that register. A register means a register has a stable value for 1 clock cycle. So at pause edge of a clock, as it shows here, a value gets from, it's a D flip-flop consisting of and as you know, D flip-flop, just at every pause edge of a clock, it takes value from the input and pass it to the output. Okay, at the output, now you have 1 full clock cycle to make sure that your signal at the output will get stable before you get a next pause edge of clock here. Okay, if for example you try to run this circuit at a higher clock, circuit will not complain. It will not say you cannot run me. Definitely you can run a system which is designed for 100 megahertz, you run it at 125 megahertz. The only thing what will happen, that you will be sampling something which is not stable. Maybe you sample a wrong value, that is what happens. Like it is 0, it needs to be 1 once it settles down, but a clock comes and it'll just whatever value you have here, it goes at the output of the register. So usually once you are synthesizing something and you try to run it at a higher clock, it will run, but it will give you all garbage. Okay, all values, and especially the paths which are violating timing. The synthesis tools are very smart nowadays. They will exactly tell you that what paths are there which are not meeting your timing. So each synthesis tool has a little calculator with it. Okay, that calculator calculates all the paths. It gets your target clock. You tell the synthesis tool, this is my target clock, I want to run this design at 100 megahertz. It says okay, 100 megahertz. Then it starts calculating. It says you have 150 paths in your design which are not meeting these timings. Okay, now you have 2 options. One is that you change your design. The other one is you start putting register in between, because you have to hop, you have to stable, I mean from POSH clock to POSH clock you have a register to register delay. And inserting registers in between, I will study how you do that. It's very cumbersome if you have not thought of it at the start of your design. Putting just registers in between is a very, very challenging problem. And the reason is there are so many paths which are running from in your design. If you try to put a register in, for example, in this path, okay, means you are stopping these values for one clock cycle. And there may be other paths which are just running parallel to it and you are not stopping them. So a register, putting a register sometimes means putting 500 registers, because putting a register in a path means you have to stop all the values in your design for one clock cycle to make sure that they are synchronized. So all these things have to be thought out. If not, then it becomes very, very challenging, very complex. Your design is not meeting timing. Your design is not meeting area, and it becomes a mess. And because redesign means many more months to actually go through the whole torture. So RTL level, if I go back and spend time, RTL level means you can put any logic, and usually people don't realize, and I'll give you an example. People say in Verilog, in C you don't care, but in Verilog you say A is greater than B, okay? For you it may be a very simple statement, but look, this in hardware mean a subtractor. You are actually checking this. It's a subtractor, and you have like tens of these. You say this minus this, or this minus this, and this minus this. It's an algorithmic statement you can easily code in Verilog, but it's a very complex piece of hardware which you are actually putting in your design. You're putting a subtractor, okay? So if else may be a simple statement coming in if else, you may think it's just, it's a logical statement, but it has a consequence because you are inferring and adders are very slow. So that's why it's always good to know what you are coding. Whenever you write a statement, you must have at least things in your mind that, oh, I'm putting a subtractor and 10 subtractors and 5 adders, and they are in a sequence, so means that they'll take time. Because you only have to guess, and you should guess and keep guessing that while you are designing and not actually coding, that okay, this is my design, do I need to put registers, so that you do it before you actually sit down and start coding things. If you don't do that, okay, you code and you say, oh, it is only running at 4 megahertz, okay, and you want to go 40 megahertz, so you are already out of the game, because taking 4 to 40 is almost impossible. It's 10 levels of registers you have to add. Okay. So these are the challenges which we need to understand before we are designing hardware. Otherwise, if you know all these things, you are designing, you have done this much work, then coding Verilog is very simple. It's maybe anybody can do it. Honestly, it's even a high school student can actually code RTL Verilog. It's that simple. So so these are the things which we need to know, that the clouds and the registers, and so Verilog will do the especially the lab. So in the lab you will learn the tools, the model sim, and how you actually code. So if I just read a few of these lines, it says Verilog you use for modeling design at RTL level, and writing stimulus for testing and simulation on simulation tools like model sim. Actually there are two parts to Verilog, and one is, usually we name this device under test. For some reason, I don't know why, but we always call it DUT, a device under test, okay? And then is something which is not under test, which is not your device, okay? Device under test is, for example, I ask you to sort out an array of 120 numbers, okay? I give you a problem. In my design, I want a very fast sorter which can just do the sorting in few cycles, and I say, okay, I'll give you 128 numbers and you give me the maximum of it, or that's the sorted list, right? So I say my interface is there is a 16-bit bus where I write, and here is this memory or the FIFO. So I just write into this FIFO 128 values, and I say you start, okay, and you this is your logic which you have designed to actually sort this list, and this is another FIFO. You put this and you say done, and I have another 16-bit bus and I read all these values, okay? So this is a little assist, because for example I am doing an algorithm where all the time I am sorting, because all the time I am sorting, I say software sorting in software is very expensive, because it has lot of if else, if else, if else, and as I mentioned earlier, if else are very expansive statements. So this is your device under test, which is actually doing this, and you need to now test it. So test is your stimulus. There are more challenges in designing stimulus than actually coding this device. Coding this device is very simple, and this is what again people miss, and always you will find out somebody will say, oh, it is working, and then after 3 days he'll say it is not working. Then again he'll come and say, now I have made it work. Then again he'll come and say, no, actually it is not working, because they never test it the way it should be tested. So the challenges I see in digital design, they are here in writing stimulus in a way that you do the entire coverage. The coverage is very different. For example, I give you sorting and you just only test for all zeros. This is a test, you say it's working because at the output I'm getting all zeros. But you have not tested the design. All zeros, all zeros. Obviously, even if you have missed something, it will never come out in your design, say it is working. People will say, oh, I have designed an adder, if you add 0 plus 1, it says 1. So it means nothing. It's just you have tested one. So challenges are in testing. And I just to expose the challenge, for example, I ask you just make a simple adder yourself, a 16-bit adder. Okay. Now you say adder, obviously you design an adder, you test it for 100 values, for example. You say, oh, 100 values, I have given 100 test vectors, it's working on 100 test vector, it means it's working. No, it's not working. Working means there are 2 raised to the power 16 possible values and 2 raised to the power 16 possible values here. This is what is mean by working. So 100 values, just now you find out that how much this is. So 216 into 216, if you give these many inputs and then you come and tell me it's working, then I'll believe it is working, because now I know it is really working because you have tested it for all the values, all the possible values. That's what people usually don't do. They do it for 1000 values, 5000 values, 10,000 values, and they'll always find out, honestly, they'll always find out there is a value for which it is not working. For example, we designed this a telemetry system, there was a codec in it, a Cordic algorithm which computes sine and cosine. I said it's working. Actually, we put everything together and we were actually testing it on the real data, and then we find out for one particular angle, there is some angle 0.931251 in radian, the design was not working for this value. It took us months to actually get down to this level of detail. That actually it comes because once it is a real system working on gigahertz speed or megahertz speed, so it will come in a day or 2 days. After 2 days, definitely going to come. And if you're devising something which needs to go on a satellite, okay, then you have no other way but just to make sure that it works all the time. For this particular input, okay, a 16-bit value, which is just its probability of happening is 2 raised to 1 over 2 raised to the power 16. But believe me, it will happen. And once it happens, the whole thing goes away. Okay, and then in our code we have to put if angle, and this was the fix, if angle equal this, then cos is this and sine is this. That was the fix, because we could not able to actually figure out why it is not giving correct value at this angle. The only thing we could do is we know that it is not giving correct value at this angle, so let's at least fix it so that it does not fail. So these are the things. The testing Verilog is really challenging. You have to be very creative while you do the testing. If you see here, as a matter of fact, I showed you this. This is called coverage, and this coverage tool is provided in most of the tools you use. Coverage, it will tell you whether the way you have tested it, have you covered everything or not. Okay. For example, I'll give you another example, and that was also a bug which really made most of us sick, because the chip which I talked about, we spent $1 million, honestly, $1 million to fab that chip, and it was not working. At a particular state, it will come and it will hang. The chip will hang. Start figuring out what happened. There was a state machine which had about 128 states. Okay, but it was an ASIC. You cannot just go change the Verilog code. You have the chip. So it was going in a particular state where it will only move in a circle. It will go to this state, then this state, this state, this state, this state, this state. It will never come out. So you have to actually reboot the system. So then we have to do things in software, making sure that it never comes in this state, things like that. We fixed it, but testing digital design is very complex, and that's why there are tools after tools which people are providing, and we'll spend some time learning about these tools. They are called coverage analysis tools. They'll give you the comfort that how much coverage have you gained, because you cannot sometimes do exhaustive testing of your design because there are so many probabilities. For example, here I just created one that you are just adding, numbers, and I'm saying, oh, you are adding, it means 2 raised to the power 16 into 2 raised to the power 16. But usually the design, you have so many inputs. Let's say you have like 16 16-bit inputs. The 16-bit input means all their probabilities is 2 raised to the power 16, 2 raised to the power 16, 2 raised to the power 16. So it becomes so many that it is humanly, or even for any machine, it is impossible to do exhaustive testing. Then you got to be intelligent. But the important aspect is that once people are designing smaller components, and they quickly jump up, they say, oh, it's working, let's now integrate it in a bigger and a bigger and a bigger, and then they start finding problem, and then they need to go down and see where the problem is. So whenever you design a little thing, try to do exhaustive testing on the little components, because you cannot do exhaustive testing on a bigger design. It's impossible. Okay, it will take many days to maybe 1 month to test a simple design with so many inputs. So it's always better that we know these things, that coverage is important, and there are tools, and we'll spend some time learning about them. So Verilog gives you provisions to write design at RTL level, write the stimulus, write the test vectors, and use a simulator, which usually we use a model sim. So that is what we'll teach you. Simulation tools typically accept full set of Verilog language constructs. Verilog is a rich language. If you download its standards, perhaps 600 or 700 pages thick of document it is. It's difficult to actually learn the entire Verilog. So it's a very thick document which says IEEE standard, which they released in 2005. But it's very small part of Verilog that actually translates into hardware. We call this RTL Verilog. You need not to learn everything, but you need to learn as much as you can. Okay. So Verilog, as it says, the whole entire Verilog is very rich. They are adding more and more functionality. But RTL design is very simple Verilog, because synthesis tools will only understand a little Verilog, and they translate it into hardware. And anything which you write outside that little Verilog, they'll get confused. They'll say this is non-RTL. I will not translate it into hardware. So the RTL design. So this is the simulation tool. The RTL design without stimulus is synthesized on target technology. Obviously, once you are actually synthesizing, you don't synthesize your stimulus. You only synthesize your DUT, which is device under test. And there are language constructs in Verilog that are ignored by the synthesis tool. So it'll ignore it. I will not complain, it'll ignore it. For example, there are timing statements you put, it'll ignore it. And then the others, it'll complain. Synthesis tool typically accept only a subset of the full Verilog language constructs, and that is called RTL Verilog. Okay. So these are the standards, and it's interesting, in 2005 they came up with another language, because the challenge is in testing. Challenge of digital design is in testing, and Verilog is not good enough to test. Very, very complex designs, protocols, and people were coming up with non-standard languages to test a design. There was an E language, then there was Vera, then there was Zero-In, okay, and they'll sell it at a very high cost. So you need to get a license. If you are doing any meaningful complex design, you have to buy one of these tools. Otherwise, Verilog is very difficult to test. So you have to, for example, I'll give you an example. You are designing a PCI interface, PCI-X interface. Okay, because PCI is a standard interface. Now you need to go to Zero-In and ask that they should give you a checker. A checker is check all your signals which you are actually using at your interface. So whatever transaction your design is making, the checker will test whether those are legal PCI transactions or not. If they are not, it'll complain. It'll file, it'll say, oh, you cannot do this. After a request, so many cycles, you need to get a grant, or things like that. So they sell these checkers, and checkers are for the standard protocols. So you put a checker in your design, and then you complain, this my PCI-X is compliant to a standard because I have used this checker, and checker is not complaining. and Checker also generate test vectors and this and that. So it was going in that direction, because something you put in a chip, people want to make sure that once it is in a chip, then it will work. And you'll not come, oh, I have not tested, this particular test vector. So the Checkers and these tools were getting very, very, very expensive, and then people were coming up so many different tools in the market. So Verilog, the industry decided to sit down and design another and define another standard of Verilog, which is called System Verilog. And the problem with System Verilog is, it's not problem, it's the power in System Verilog is, it is for the hardware design, for the specification and verification. They mix everything in one language, and that is what it makes it very, very complex to learn and very complex to use. And no synthesis tool usually at this point, it supports System Verilog. No, for example, Xilinx will not support System Verilog. Okay, so and now what you can do is you design your device in Verilog and your test vectors in System Verilog. And those of you who are good in programming languages, System Verilog offers you like classes, its inheritance, and all the concepts in object-oriented programming, and even more than that, the coverage, the way you can steer your test vectors, bias them in one direction, bias them in another direction, randomize them. So they added all the power in all those tools in System Verilog. So we'll spend a little time in System Verilog as well, so that for testing, those of you who are testing complex design, System Verilog is something very good, and same is the case with System C. But System Verilog, Model Sim supports System Verilog. So simulation is done in Model Sim, it supports System Verilog. So for whether it is System Verilog or Verilog in hardware design, let me just show you this, and then I'll get back and do the usually this is how a hardware design is structured. A hardware design is structured in a way where you have components, okay, like for example, this is a communication system which we entirely coded on an FPGA. Okay, it is from the documentation. I've just copied the drawing which the engineering team at that point crafted. So it has, as you can see, it's a serial clock and the serial data. It is getting into the device and it is going to the AES. So very first block was encryption block. So we'll do encryption on this, and once encryption is done, then we do forward error correction encoding. When encoding is done, we do the framing. Once framing is done, we do the actual modulation, multiplying it with an exponential, and then passing it to a D2A converter. So this is how a typical design in hardware is done, that there are blocks. A block has few inputs and few outputs, right? So because they are real signals, so you don't have pointers and abstract classes. Those System Verilog supports all these things. But usually in Verilog, because all these are physical wires, whatever you write as input and output, they are physical wires which are getting into your system. You process and you generate output, those are also physical wires. Then these are the physical wires you connect to components. As you can see, this component is connected to this component through a wire, or this component is connected to this component through some wires. Okay, so that's how the Verilog is also structured, that you have a top level design. A top level design is a big box which basically has all of these, and then the the input signal to that box is just a serial clock and a serial data. So every POSH clock you get a bit. So you have to collect all these bits to make a word. So because a serial interface, that's what you have. And then it's a D2A interface, you have a 12 bit of data at a clock. So at a clock you throw 12 bits, 12 bits, 12 bits, all the time you are doing this. So this is your, at the top level, this is how the module is. Then inside a module you have smaller modules, and many of them. For example, this is an AES module. So AES module again has few inputs and outputs, and you can see what all inputs you have in an AES. You have an AES interface, and then you have this FIFO module. And this FIFO module, you have many copies of this FIFO. So there may be modules where you have several copies, and there may be modules where you only have one copy, but it has its own character. AES has its own character. You never try to mix AES with FEC because they have different character, and that's how you design, test. So in Verilog, you need to think in terms of components. Okay, and you think in terms of component, and while you are designing on the drawing board, you make these boxes, and each box is defined in a module. So basic building block is a module, and the modules basically you declare them and you instantiate them, and in Verilog you cannot nest module declaration. I mean, inside a module you cannot define another module. In system Verilog you can do that. Okay, so a module you can instantiate other modules, but you cannot declare another module. So module is, you write module, you write its name, you give port list. So there are two ways to define port list. Either you give port list and declare it here, or the other one is you declare the port list as you do in C, right in the module definition. Okay, so let's see, this is an example where you say module full adder, and input A, input B, input C, carry in, output sum, output C out. So this is how a module is defined, declared. It may be as simple as a full adder, it may be as complex as a Pentium processor. So Pentium processor module will be module Pentium processor, and there are thousands of ports. This bus, that bus, this line, that line, this clock, that clock. So that will be the top level module of a Pentium processor. Okay, so but this is how a module is defined, and inside you give the functionality. So module definition is like this: you have inputs and outputs, and usually in Verilog it's again important to structure your design, and we say that we use hierarchical design concepts in Verilog, because it's not software, it is hardware. Hardware is physical thing which you are designing. So it is going to be something physical. So, and we always think in terms of physical modules, so we design it in hierarchical manner. Hierarchical manner means there is a top level module, then there are smaller modules, inside smaller modules, there are even smaller module and smaller modules. So sometimes you think in terms of top to down, and in other way you say I have this smaller module, I put it to make a bigger module and a bigger module and a bigger module. So you go both ways, it goes both ways. But hierarchical design means that you can go from top level to the bottom level, and the bottom level to the top level. Okay, so these are the two ways of designing a module. A module where you only write port list A, B, C in, sum, C out, and then you come down and say these are my inputs and these are my outputs. And other ways, right here you say inputs are A, B, C in, and output are sum and C out. This was supported by Verilog 2001. Initial version of Verilog only supports this. So, and then you can use this module. Again, I have used very simple example, because the focus is to learn how you define module and then how you instantiate them to make a bigger module. Okay, so you have this full adder module, and now you want to build a 3-bit adder, for example. So you have A, which you write 3 bits, B 3 bits, C in 1 bit, C out 1 bit, and sum 3 bit. Again, it's always very useful to think of your design in terms of boxes, and always draw these figures in your design document, so that people can comprehend how you have structured your Verilog code. Otherwise, reading and comprehending Verilog code is very complex. In the same reason, because it is hardware, the things are happening everywhere. It is not like software that you can just go through the software sequentially. In hardware, things are happening at every point. So if you don't put thoughts in your design, if you don't document them properly, if you don't comment them properly, if your variables names are not comprehensible, it's very hard for people to understand. Always you will find person coming and saying, I cannot understand it, so I'll recode it. So means the efforts you have made for 6, 7, 8 months, 1 year, people would just throw this away because you have not documented it, you have not commented it, your variable names are not making any sense, and means that all your efforts, somebody will just trash them, and they say it's better that I, instead of understanding this honestly, and it's always the case, it's better I'll do it in a month and then I'll go and make modifications. So again, adhering to these guidelines, they are very important. So you say A0, B0 goes here, A1, B1, A2, B2 goes here, carry 0, carry 1, and so you make all the interconnection. And then if I go back, this is the basic module, which is actually adding 3 bits and producing 2 bits, A plus B plus carry in, and giving you sum and C out. Sum is the least significant and carry out is the most significant. And again, as I mentioned, I know most of you already know Verilog. Those of you who need more help, so we'll do a workshop, an exclusive workshop. We'll spend more time. So I'm very quickly going over this material. So full adder is one instance. So you write the module name and the instance name. And this is one way you, because if you know, remember that your actual module has ports A, B, C in, sum and C out. But now because you have 3 instances, then definitely all these 3 instances are going to have different inputs, their names. So first module has this input A0, B0, A1, B1, A2, B2. So one way is that you put dot the actual name and the name which you are using in the current instance. This is an easier, more convenient, more comprehensible way of instantiating a module, that you put a dot, write the name, dot, write the name, dot, write the name of your inputs, and dot sum, then this is the actual sum 0. So you write a full adder module, its instance full adder 0, full adder 1, and full adder 2. So 3 instances with these names, and this is your whole design. So a bigger box and then smaller boxes. So a good design usually is, I always think, and you must always think in terms of a bigger box is your top level module. As long as you can keep up with this practice, then you have a smaller boxes and smaller boxes in it, and inside smaller boxes you have even smaller boxes. So this is the hierarchical design aspect of Verilog, that you structured it in a way that people can easily go through as much as you can. So definitely a module, ultimately a box is going to have a character, a functionality, but this is usually what you see. So many smaller modules and their instances. So partitioning, I have already told you that partitioning is very important. At system level, you need to break your module into smaller boxes, and a mix of top level and bottom up methodology is practiced. And these are the guidelines, and these are important guidelines in hardware design. And why these guidelines are important, and I will just, because I would spend rather more time in stressing on the guidelines and then on the actual syntax. The issue is, once you have a bigger design, there are maybe 10 engineers working on it. So you break it down into 10 parts. You say you do this, you do this, you do this. Always it is like this. So you have a bigger design, and you say, because it's a bigger design, so you divide it into 10 engineers, and you tell them, okay, this is how you need to work on these modules. So usually the person who is actually partitioning the design, he must make sure that each design must have all its outputs registered. And the reason is, the timing is always register to register. And okay, once we say timing, then somebody comes and claim that my design is working at 40 megahertz, and you want to make sure, this is the target clock which you are given to 10 engineers, that design must work at 40 megahertz, because this is my target speed in my mind, that I want to make this chip work at 40 megahertz. So every design, even there is a single path which is not working at 40 megahertz out of million paths, you are in trouble. Right? So you say every engineer design must work at 40 megahertz. So you partition a design in a way that outputs are always registered, so that once you put another module done by another engineer or by the same engineer even, and now you synthesize, because timings are from register to register. Okay, if registers are at the output and this block is working at 10 megahertz and this block is working at 10 megahertz, then it is guaranteed that the 2 blocks will also work at 10 megahertz. Why? Because we can see the timing from register to register. There may be other registers inside the module, but if this is not the case, and a person has designed something where it has a logic and number of registers and then again combinational logic, and he comes and tells you, oh, my design is working at 40 megahertz. Okay, and now you put another person's module here, and he has also a combinational cloud. Okay, now the register to register timing is from this register to that register. So this logic was working at 10 megahertz, this logic was working at 10 megahertz, but once you put them together, it becomes a bigger combinational cloud, and it may only be working at 5 megahertz, and now you have problems. And now you have problems very difficult to fix, because somebody has not really catered for this, because an individual engineer is only focusing on his part, that yes, my design works at 10 megahertz. So this must never be the case. If this is the case, there is something very seriously wrong you are doing, that your outputs are not registered. it means there is something, there are problems which are calling for problem. So this must be always the case that all your outputs must be registered. So as is shown here, here are registers, here are registers, here are registers. So you adhere to this coding guidelines. I'll help you to make sure that once you put, this is again a very ugly way of writing Verilog. Usually what people, top level design must have no other logic but smaller modules inside it. Okay, because at top level you have